Assalamu alaikum. Let me start with the beginning. Okay. So, last time we studied unit sample sequence. Now continuing with various discrete time signals. So last time we had discussed unit sample sequence. So it's a signal which is having a value 1 at sampling instant n is equal to 0, and it has a value 0 apart from that. So it has a single value, that is the 1 at n is equal to 0. Apart from that, at everywhere throughout the axis it is 0. Right? Now you have a unit step sequence. So let me, this is again the mathematical interpretation of this, but let me just explain you with the help of diagram. Okay. So a unit sample sequence denoted by UN, unit step sequence, basically. A unit sample sequence, like unit sample sequence, is denoted by delta n, or it's also called delta sequence. This is unit step sequence is denoted by UN, right? So it is equal to 1 at n greater or equal to 0. Fine. It is equal to 0 at n less than 0. So n less than 0, it will be always 0. Fine. This will be equal to 1 up to infinity. Fine. It will be throughout equal to 1 after n greater or equal to 0, starting from at n is equal to 0. This is a unit. This is what I have shown mathematically. So this is 1 equal to n greater than 0, n less than 0. Clear? Now again, it's suppose you have 10 samples. The unit step sequence of 10 samples is written by this. See, for example, this is a sample sequence at -2. It's a sample sequence at n is equal to -1. It's a sample sequence at this arrow point. It's a sample sequence at n is equal to 0. After that, n is equal to 1, n is equal to so on and so forth. Right? So this is a unit step sequence. This is the diagrammatic representation of it. Okay. Now let's move forward. Okay. Now you have unit ramp sequence. So at a unit ramp sequence, it's denoted by u subscript n, and it is equal to n for n greater or equal to 0. It is 0 other than that, n less than 0. So this is a unit ramp sequence. So at 1 it is 1, at 2 it is equal to 2. So you see, it is u2 is equal to 2, at 3 is equal to 3, at 4 is equal to 4, at 5 is equal to 5, at 6 is equal to 6, at 7 is equal to 7. So less than 0, it is always less or equal to 0. It is less or equal to 0, it's always at. So at 0 it will be 0, u of 0 at 0. So less than 0 it will be again 0. Fine. After that, it is equal to n. So it's a unit ramp. So u of 2 is equal to, likewise, u of 10 is equal to 10. Right? Clear? It's just that it's increasing. Right? It's increasing because n is increasing. Clear? Oh. Now let's move to exponential sequences. So an exponential sequence is denoted by this: xn is equal to a raised power n. Now there are two types of exponential sequences. One is the decreasing exponential sequence, and another one is the increasing exponential sequence. When you get a decreasing exponential sequence, when a is, see, it is a raised power n, then you have a lying between 0 to 1. Obviously, with the increase of n, the value of xn will decrease, because xn is equal to a raised power n, right? When a is less than 1, it is between 0 to 1. So with the increase of n, what will be xn? With the increase of n, a is less than 1, it's between 0 and 1. With the increase of n, you will get a decreasing exponential function. Fine. For example, see, n is less than 1, that greater than 0. For example, we will take an example. a you will take as 0.2. Fine. So you will have uh, uh, a point to n. So with the point to n, right? So with the increase of Cn, this xn will decrease because it is less than 0. Fine. So you'll have 0.21 raised power 1 is 0.2 again. So 0.2 raised power 2 will be 0.04, 0.04. So with the increase of n, your xn is decreasing. That is a decaying x. But if a is greater than 1, for example, then with the increase of n, what will happen? Your xn will increase, right? So this is a is greater than 1. This is a. With the increase of n, when a is lying between, simple mathematics. With the increase of n, when your a is lying between 0 to 1, it will, with the increase of n, your xn will decrease because it's a raised power n. Fine. But when a is greater than 1, with the increase of n, your xn, so here is gn. Fine. Your gn will increase. So this is increasing exponential function. This is decaying exponential function. Clear? Okay. Now exponential function, exponential sequence, sorry, it can be a because why is sequence? Because we are talking of discrete signal. That's why it's a sequence, not a signal. Right? So the exponential sequence can be a real valued or it can be complex valued. Clear? Now, if a is a complex valued, then you can represent a is equal to r e raised power j theta. Right? Now, what is r? R is the magnitude of a, and theta is the angle of a. This you must be knowing from complex numbers. Fine. So r is the magnitude of a and theta is the angle of a. Hence, when you substitute this value, see it's a raised power n. Instead of a, I write r e j theta raised power n. So rn e raised power j theta n. Now apply Euler's identity. What is that? E raised power j theta is equal to cos theta plus j psi theta. See, now here r raised power n as it is. Instead of e raised power j theta n, I will write cos theta plus j psi theta because it is raised power n. This n will come here. Fine. J sin theta n. It's j theta n. So after expanding, you will get cos theta n plus j sin theta n. Right. Multiply rn. Fine. With both cos and sin. So you will get rn cos theta n, rn sin theta n. Now this has a real part as well as the imaginary part. What will be the real part? This will be the real part. What will be the imaginary part? This will be the imaginary part. Simple complex numbers. So this will be the magnitude of a. This will be the theta n will be the angle. Right? See. So the real part of xn, that is x subscript r, that stands for real, is equal to rn cos theta n. Imaginary part, that is xl subscript n, that is r sin theta n. Fine. Now magnitude of xn, that is modulus of xn, that is an. What is that? That is rn. This thing. This thing is the magnitude of xn. Fine. Now phase, that is the angle of xn, is the theta n or phi n, but instead of phi here is theta. So you will have theta n. Clear? So magnitude of xn is modulus of xn, that is an, and that is this. This is the magnitude, right? And then you have the imaginary part of xl. This and imaginary part of xl is imaginary part of xln. That is sorry, the phase of xn. Phase of xn is phi n. Here it is theta n. Clear? Okay. Now you have to prove this thing. You have to prove that what is delta s? It's a unit sample sequence. You have to prove that this is equal to. First, you have to understand what is this. See, this is mathematics. It's very hard for me to write it in PowerPoint presentation and to help you understand it. See, had I been giving my lecture on a blackboard, it would be much simpler for me as well as you to understand. But till now, we have to adjust with what is available to us. Okay, so this is Okay, what is this delta n? I will try my level best. Still, I will try my level best to make you understand. Fine. So, what is this? This is delta n. What is delta n? It's a unit sample sequence. This you have to prove un is equal to minus un. Okay. Now, before I will prove that, first tell you what is un. It's a unit step sequence. You know that unit step sequence is equal to 1 for c. See, this is a unit step sequence. So its value is 1 from n is equal to greater or equal to 0. This whole thing. So it will be less than 0, it will be always 0. Fine. Greater than 0, it will be always 1. See, in the example, it's given un minus k. Instead, if un minus k in your example, it is un minus 1. That means this is a delayed sequence. Your unit step sequence is delayed by one step. See, by what do I mean by that? So instead of 0, your delayed sequence will start from here, right? It will start from here. Suppose here it is 1. See, it's minus 1, 0, and when I delayed it by one step, here it's k. Instead of k, it's 1. Take example, it's 1. Fine. So when I delayed it by one step, it will start from here. So here also you will get 0 at un minus 1 will be equal to 0 when n is less or equal to 0. Fine. Here it was equal to 0 when n is only less than 0. Then it was n is equal to n is this un is equal to 1 when n was greater or equal to 0. Here it is equal to 0 when n is less or equal to 0. Fine. Now it is equal to 1 when n is less or equal to 1. So it will start from, suppose here it is 1 instead of k, here 1. So it will start, your sequence will start from 1. Sample sequence, sample instant 1. So it will start from here. See. So this is what I have shown. So un is equal to 1 when n is less or equal to 0. It's equal to 0 when n is less. Now un minus 1, it is equal to 1 for n greater or equal to 1. It is equal to 0 when n is less than 1. So less than 1 is 0, minus 1, minus 2. So it will be always equal to 0. When you subtract these two, you should get a delta function. See? Now, when I subtract this sequence from this sequence, this whole thing will get nullified. This will get cancelled out. This see the signal, the step sequence, the sequence at this will get cancelled by the sample at this. So you will get a delta signal which is having a value 1 at n equal to 0 here only. See, are you trying to understand? See, once more. See, this is this is what? This is a unit step sequence and this is a delayed step sequence by one factor. In the example, it's k. So suppose here it is 1. Now when I delayed it by 1, I subtract this from this. So you'll get only this stick, right? You'll get only this stick. Why? Because rest all these sticks running from 1 to infinity, they will cancel out from each other. You are subtracting it. Hence, you will get only a signal whose value is 1 at n equal to 0, and that is a delta sequence, your delta function. So this is, it's here, right? So this is what I have written here. So it's equal to 0 for n less than equal to 0. It's equal to 1 for n equal to 0, and it's equal to 0 for n less than 0. So less than 0, it will be 0. Greater than 0, it will be 0. At 0, it will be 1, and that is a delta function or unit sample sequence, a delta sequence or unit sample sequence. That is delta, and hence proved. So for practice, you will also prove these two. Just try to understand. simple. You have to use simple logic. Fine. Substitute the value of take right hand side. Just now just like I took right hand in the previous example and proved that is equal to, use your brain guts, and you have to prove that this is equal to delta k running from 0 to n. And similarly, in the second example also, you have to prove that k is running from 0 to infinity, and this is delta, and it's a delayed sequence. Delayed by how many units? K units. It's a unit sample sequence. K running from minus infinity to n. Fine. Okay. That's all for now. Okay. Assalamu alaikum.